12 General 2.2 End of Term Revision. KPI 2.2.5 explain the process of charging two neutral spheres with a charged rod by induction. So here I approached by induction a negatively charged rod. So the electrons will be repelled, will get repelled and sit on the sphere number 2 and leaving positive places for rod number 1. If I separate them, sphere 2 will be negative and sphere 1 will be positive. So 2.2.7 regarding the work of an electroscope, here we have the diagram below shows a positively charged electroscope. So it has a deficiency of electrons. Explain what happens to the leaves of the electroscope when rods with the following charges are brought close to but not touching. So it means also by induction. So if I approach a positive charged rod, this means that, so for the first one, if my rod is positive, this means that electrons will go up and get attracted to this positive charged rod, meaning that they will leave more empty spaces, more positive spaces. So this means that the two leaves will be even more positively charged. Okay, so this means that I can say that the same thing I was saying, that electrons they will move up. So this means that the leaves will become even more positive. The leaves will be more positive. So this means I will have more repulsion. More repulsion. Now the second one, if the rod is positively charged, let's see what happens. If the rod is negatively charged, this means that the electrons on the sphere will get repelled and they will go downward. And this means that you will here have less positive here. You will have less positive leaves and there will be less repulsion. So they will fall. So I can say that electrons, they will move from the top down to down, and this means that the leaves will get less positive. Less positive, this means leaves will fall. Continuing, state the magnitude of the elementary charge. So the elementary charge is the charge of one electron, and the total charge is always a multiple of this elementary charge. Question number 16, which of the following is not possible value? Not possible value, this means it doesn't follow this rule. So eventually the charges here that I have are all given charges, Q's. So let me test is if this Q equals to NE. If N is not integer number, a whole number, this means that I cannot have this charge. So let us try it. 8 10 to the power of negative 19 equals to n multiplied by 1.6 10 to the power of negative 19, giving me that n, certainly here in an absolute value, n equals to 5. So yes, I can have 5 electrons. But going to the correct answer, here also Q equals to NE. So negative 8.8 10 to the power negative 19 equals to N 1.6 10 to the power of negative 19. While here, it corresponds to 5.5 electrons, which I can never have. I cannot have a decimal numbers of electrons. They always come quantized, integral multiple of the elementary charge. So this one is not possible. So it is D. Use vector addition to calculate the net force. Here let us discuss the direction of the force. What is the direction of the net force by charges A and B on C? So I'll talk about C. So as I can see that charge A is negative, charge B is negative, charge C is also negative. So talking about A and C, C will experience a repulsion by A. So that's the force done by A on C. Also, B and C are negative, so C will also experience a repulsion by B. The net force is toward the right. Now, applying Coulomb's law, the interaction, the action-reaction of the electric force between two charges. For example, here, what's the magnitude of the electrostatic force between the two charges, charged sphere? So it is described by F equals to K, which is 9 10 to the power of 9. The absolute value of A, absolute value of charge B, divided by the distance between them squared. So F equals to K QA QB divided by the distance squared. So 9 10 to the power of 9 times 1 10 to the power of negative 6, 1 10 to the power of negative 6, divided by 0.4 squared. The answer is, in Newton, 5.6 10 to the power of negative 2 in Newton. So because they are both positive, this means A will repel B to the right, and B will repel A by the same force, exact same force, but to the left. Now let's have some additional practices for 2.2. The leaves of negatively charged electroscope diverge more. So we have a negative electroscope, all negative. They diverge more when an object is brought near the knob of the electroscope. The object must be, so basically I need to have electrons going down, so it should be negative. Negative electrons going down for further repulsion. Question 8. Also here I approach a positive charge. So this means that negatives will accumulate on A and leaving B positive. So the correct answer is that the sphere A will be negatively charged and B positively. Here I have a positively charged rod brought close to the top of a neutral electroscope as shown below. Which of the following show the charge distribution on the electroscope? So it is a neutral electroscope. When it is a neutral electroscope, this means that electrons will be attracted by the positive rod, meaning that the knob will be positive and the leaves will be bipolarization be positive. Question 11. A positively charged rod brought close to a charged electroscope. What is the charge on the electroscope? Negative if the leaves fall. So electrons will go up attracted by the positive rod. So negative if the leaves fall, yes. If it was negative and electrons go up, this means it becomes less negative. Positive, let's read the second one. Positive if the leaves move apart. Yes, of course. If it was positive and electrons leave down, so it will become more positive. Negative if the leaves don't move. No, that's not correct. So only 1 and 2. A positive and a negative charged rods are brought one at a time close to the cap of a positively charged rod. So here I have electroscope. Here I have an electroscope that is positive. When I approach a positive rod, this means that electrons will go up, attracted by the positive rod, and these two leaves. So this means that down will become even more positive. So this means that I will have further, let me draw it in red. So this means that I will have even more positive down because electrons, they are moving. So the leaves, they will move away. So here, let me say away. For negative charged rod, if I approach, let's say, a negative rod, electrons will be repelled downward by the negative charged rod, and here the leaves will become less positive and they will move, they will fall. So option A will explain, will give me the correct answer. What is the unit of the charge? It is the coulomb. How many electrons does it take to make 2 coulombs of charge? So given Q, so Q equals to NE, it should be a multiple of the elementary charge. I have 2 and 1.6 10 to the power of negative 19, giving me that N equals to 1.25 10 to the power of 19 electrons. So option D. Question 17. 2 charged spheres are held a distance r apart as shown in the figure below. Compare the force of sphere A on B with the force B on A. So by action reaction, disregarding like the size or the mass or the charge of on each sphere, by action reaction, the force on A should be equal and opposite to the force on A. So giving me the first option. 3 charges A, B, C are located in a line shown. What's the net force on charge B? So I can see that A is positive, B is positive, C is positive. So on charge B, so A will repel B to so I'll call it FA. So A will repel B to the right, and C, because C and B are also positive, C will repel B to the left. However, here, let me first find the force done by A. So it is KQA QB over the distance between them, 4.2 10 to the power of negative 2 squared, and the force done by C, KQB QC over 2.9 10 to the power of negative 2 squared. And once I have each one, so by replacing them by their values, 10 over 9, the first is 8.6, 8.5, 10 to the power of negative 6, 3.1, 10 to the power of negative 6, divided by 4.2, 10 to the power of negative 2, the whole thing squared. The second one is 9, 10 to the power of 9, 3.1, 10 to the power of negative 6 by 6.4, 10 to the power of negative 6, 2.9, 10 to the power of negative 2, the whole thing squared. After finding each one, I will deduct them. So it is 8.1 times 3.1 divided by 9 times 10 to the power, 10 to the power of 9. So the first one is 134 Newton, and the second one 6.4 divided by 2.9. The second one is 212 Newton. So this one is 134 and this one is 212. So basically, because they are in opposite directions, the net force is the difference. So FC minus FA, it will give me 78, and the larger is the 212. This means it is toward A in this direction. So F net is 78 toward A. Later, the force between a charge of 15 microcoulomb, so that's Q1. Don't forget to convert. On a charge that is minus, this is Q2, is I have the force. I need the separation between the charges. F equals to KQ1, Q2 divided by the distance squared. 6 is 9, 10 to the power of 9, times the first charge 15, 10 to the power of negative 6, 5, 10 to the power of negative 6 divided by the distance squared. It will be 0.34 meters. Question 20. If F is the magnitude of the force between 2 point charges when their separation is d, what will be the new force if the separation distance is doubled, while each charge is reduced by half of its value? So Q, each one is halved, Q over 2, Q over 2, and the distance is doubled. So remembering that F is proportional to Q first, the second Q divided by the distance squared. So in the calculator, I will put the first one halved, the second one halved, and down I will put 2 squared. So that's the change that I have. So it will be 1 over 16. So that's the change that will occur. So F will be reduced to the 16th. True or false, the charges exert force on other charges at distance, which is totally true. The force between charges is stronger when the charges are closest together. That's 100% true. If a charged rod brought close to an electroscope has a similar charge, close means by induction of similar, then the leaves will fall closer. That's not true. They will fall further. Force between two charges is directly proportional to the square of the distance. That's wrong. It is inversely. The elementary charge is this much. That's true. An object with a net charge has 3 excess electrons. Let us see, this is Q equals to NE, -4. So the excess is okay because it is negative. Let's see if 3 is correct. 10 to the power of -19 equals to N times 1.6. 10 to the power of -19, that's 3. So true. An object with a net charge of has 8.8, 10 to the power of -19 has a deficit of 5 electrons. That's not true because we tried it and the answer was 5.5. Again, so 8.8, 10 to the power of -19 equals to N 1.56. So N equals to 5.5. So it's not 5. So it is false, not true. Thank you.